Hello, everyone, and welcome to my talk on improved approximations for Euclidean k-means and k-median. My name is Shyam Narayanan, and this is joint work with Vincent, Cohen-Addad, Hossein, Esfandiari, and Vahab Mirrokni. So as a quick outline, first, I will provide an overview of clustering. I will then talk about our results. I'll then describe the previous techniques and what they were able to obtain. And finally, I'll describe our techniques and how we were able to improve over previous techniques. So first, let's begin with clustering. So as perhaps many of you already know, clustering is one of the most important and fundamental problems in unsupervised learning. And roughly, the question asks, if you have a data set of points, you want to group them into groups where in every group, the points are closely related, but in different groups, the points are less closely related. So for instance, maybe we have a bunch of images like these, and we want to group them together into 4 clusters. Well, we can do it as follows, and it turns out that I've grouped them into groups such that every cluster has the same species in it. So we can now talk about Euclidean clustering, which is the main type of clustering that we will be focusing on. So we think of the data as being embedded in Euclidean space R to the D. Think of D as very high dimensional. So this is a high dimensional Euclidean space clustering problem. And given some points x1 through xn, which are our data points, our goal is to find k-centers, C1 through Ck, to minimize the following k-means objective, which is the sum from j equals 1 to n, or the sum over all points xj, of its minimum distance from xj to its closest center squared. And there's also a related k-median objective problem, where instead of d squared, it would be just the distance to its closest center. And basically what this means is we want points to be very close to some cluster center on average, because we're saying that on average, the point xj, its squared distance or its distance to its closest center is quite good. So as an example, maybe we have a data set like this, then we can split it into 3 clusters as follows. We have a red, an orange, and a blue cluster. And importantly, the cluster centers, such as this orange cluster center, was not actually part of the data set. And that is fundamental. We will not force the cluster centers to be part of the data set. So k-means is a very well-studied problem. And it turns out that there's been studies on this dating back to 1957 with Lloyd's heuristic, which is known to be very good in practice, but quite bad in theory. In fact, it has basically no provable guarantees. The goal in theory, because we're algorithmists and we're theoreticians, is to find some sort of k-centers in polynomial time with provable approximation ratio to the optimum objective. In other words, what we want to find k-centers, so the objective on the previous slide is that some constant times the best possible or the minimum possible objective. So there's an algorithm called k-means++, which is known to be a very fast randomized algorithm, and in expectation achieves an O of log k approximation. To obtain O of 1 approximation algorithms, there's basically 2 major methods. The first method is local search. And the idea of local search is we start off with some k-centers, and we keep trying to replace O of 1 of those centers, or a small number of the centers, with some better centers to get a better objective cost. And we keep trying to do this until we can no longer do it. There's also the techniques of primal duo, where we try to relax the k-means problem to a linear program and find a primal and a dual solution that are close in cost. And we can use this to get an O of 1 approximation algorithm. And we are going to be focusing on the primal dual method because that's our techniques for getting the best approximation algorithms. So the main question that we are interested in is what is the approximation factor that we can get for k-means? So both Euclidean k-means and k-median are known to admit O of 1 approximation algorithms. However, they are APX hard, which means that you can't get a 1 plus epsilon approximation algorithm for some reasonably small constant epsilon. So the main question that we're interested in is what is the best approximation algorithm that we can obtain in a polynomial time? So our results are as follows. So we are able to obtain an improved primal dual algorithm for both Euclidean k-means and Euclidean k-median. And this improves over a major result of Amarian, Nerozifard, Svensson, and Ward. And we have highlighted our results in this table as follows. So we get a 5.912 approximation for k-means, which improves over the previous best of 6.129. And we also get a 2.406 approximation for k-median, which improves over the previous best of 2.633. So interestingly, our first we provide the first approximation below 6 for k-means, and we provide the first approximation below 1 plus root 2 for k-median. And even though 1 plus root 2 wasn't previously known how to be achieved, it turns out that our main contribution is really in breaking this barrier rather than in obtaining this barrier. So overall, we follow two main steps, which are as follows. The first step is to provide a better LMP or Lagrange multiply preserving solution. And we're able to provide better LMP solutions for both k-means and k-median. If you don't know what LMP solutions are, that's fine. We're going to describe them more in detail later on. The next thing we need to do is we need to convert this LMP into a k-means or k-median solution. And it turns out that previous results were able to show that their LMP method can be converted with no cost blow up. Unfortunately, we don't get that. We will have we'll have a slight blow up in the k-means as opposed to the LMP approximation. But the blow up is so small that we still obtain an improved k-means approximation. So for this talk, I'm just going to focus on the first step, which is to get a better LMP solution. So now let's talk about what are LMP solutions. So it's well known that there are some standard primal and dual LPs for k-means. And the main difficulty in these LPs is because you have a constraint that you need exactly k centers. And the way that we simplify this is we relax the linear program by allowing the number of centers to vary, but we're going to assign a cost lambda for every center. So in other words, we can have more centers if we want, but we have to pay some price for every center that we add. So we're going to, for simplicity, assume discrete k-means, meaning that we have a set of a finite set of facilities that we call F, which are the potential centers. So we have to choose k centers or some number of centers from F. And we also have a set of clients, which is just our data set x1 through xn. So the dual LP is going to be to maximize the sum of alpha j, where this alpha j is some dual variable for every client j, subject to two constraints, which is that first, for every facility, and these can even be facilities which were not chosen as centers, the sum over j of the maximum of alpha j minus d of ij squared and 0 is at most lambda, where lambda is the cost of every center. So this cost here. And also, we need to make sure that for every client j, the alpha j is a non-negative variable. So I've just rewritten the LP here. And what we're able to, a very important property of this LP is that for every set of facilities S, the sum of the alpha j's minus lambda times the size of S is at most the optimum size of S means solution. In other words, even if S does not have size k, this linear function of the dual variables is at most the optimum solution where you only allow at most size of S clusters. Meanwhile, it's not hard to show that the cost of S is exactly the sum of d of j comma S squared, where d of j comma S just means the minimum distance from j to some chosen set in some chosen facility in S. So our goal is to find some set of facilities such that the cost is at most rho times this this linear function of the dual variables. And this is basically what an LMP solution is. Basically, if we can get a better approximation rho, then we're getting a better approximation for the LMP algorithm. And the reason why this is useful is because as we increase lambda, this is sort of like increasing the cost of every center, so we add fewer centers. So this means that for the right choice of lambda, we might be able to get a set S of size exactly k. It turns out we won't quite be able to get this, but we can still use these ideas to get a very small blow up in the approximation algorithm. So the previous methods for LMP are as follows. So first, I've just rewritten the linear program as follows, and I've rewritten the goal. So we want this cost on the left to be at most rho times this sort of dual linear function, which is known to be at most the optimum. And importantly, we don't need S to be fixed. We can think of S as maybe having size k, maybe it has size greater or less than k. That's fine. So there is a technique that is used to grow the dual variables alpha j. And we're going to be using the same method. And basically what this means is we find these dual variables and make them large so that this sum of alpha j is as large as possible. And we're also going to choose S to be a subset of tight facilities. By tight facilities, I mean, if you look at this constraint here, well, this constraint is for every I and F. And for some of the constraints I and F, this inequality here is going to be exactly tight. So for those facilities, we call them tight. And we're only going to choose tight facilities or some subset of them to be part of our final set S. We need a pruning method, finally, to be able to choose which facilities in S we actually choose. And it turns out that for these tight facilities, because we're only choosing them, we can actually rewrite this linear function as something that's a sum over J and S of this quantity right here. And this will become very useful because this is a sum over J and S right here. And at the same time, this is J and X, and this is also a sum over J and X. So we can basically remove the sum and just consider an individual client J one at a time. So now we just have to compare the two things that have been circled in blue. So let's just recall what we want. We want this left-hand side to be at most rho times this alpha j minus the sum over I and S of the distance squared from I to j being at most alpha j of alpha j minus d of ij quantity squared. And this just turns out to be what we want. And we need to choose S so that, at least on average, or preferably for every point j, this inequality holds. So as sort of a visual diagram of what's going on here, because this right-hand side is very complicated, we can think of j as being some client. We have a ball of radius root alpha j, and then we can consider the facilities, say I1, I2, and I3, which are in the set S. So the distance is just the distance from j to I2 because that's the closest closest center. And we also have this alpha j minus, we have to subtract sort of something that is sort of like the distance between each of these centers to how far it needs to go to reach this ball of radius root alpha j. This is not quite correct because we're dealing with squared distances rather than distances, but to a first order approximation, it's a pretty good intuition for what we should be thinking. So in other words, what we want is we want this distance from j to I2 to be small, but we want also these distances to also be small. So the idea is that if S is too large, then the right-hand side can actually be very small or even negative because we have too many of these like blue lines like this. On the flip side, if we choose a much smaller set of S, maybe then what can happen is the left-hand side can actually be so large because there's no, the closest center is maybe all the way out here, and that can be much bigger than the right-hand side. So we need some sort of happy medium to make sure that the size S is of reasonable size. So the previous method for doing this is based on independent sets. So for simplicity, I'm going to assume alpha j is 1 for all j. And the previous algorithm is to define what's called a conflict graph, which we call h of delta, on the tight facilities. So the tight facilities are precisely the set of facilities that we're allowed to choose for the final centers. And we draw an edge between two tight facilities I and I prime if their squared distance is at most delta. And the idea is we choose delta to be roughly 2.178, and we choose S to be some maximal independent set of h of delta. And we can use some basic properties of Euclidean space, as well as we can use some results that are known based on how we grew our dual variables alpha j to show that this desired inequality holds for rho roughly 6.129. So don't worry too much about how the method of growing alpha j is, but just trust me on this fact that it has been proven in previous works. And what's very nice is that this can only be tight if the number of points I and S that have distance squared at most alpha j is either equal to 0 or 2. So what this means is that maybe if we can somehow make sure that this size is not equal to 0 or 2, we can actually get something better. So this motivates our better pruning algorithm, which is to choose a better set S. And the idea is, well, if we define n of j to be the set of facilities that have squared distance from j at most alpha j, then the bottleneck might be when n of j has size either exactly equal to 0 or exactly equal to 2. So maybe we can average over two independent sets, and maybe the average value of n of j will become 1, and you can maybe say that this will not become a bottleneck, so you'll get a better algorithm. So from this motivates our first attempt, which is as follows, which is to choose some parameters delta 1 and delta 2, which straddle the sort of previous best delta, which was about 2.178. And we're going to choose first a maximal independent set of h of delta 1. So this is the bigger conflict graph because delta 1 is bigger, but because it's a bigger graph, or in other words, it has more edges, it's going to have a smaller independent set. And then we can extend it to a maximal independent set I2 using h of delta 2, which has fewer edges. So the final set that we're going to choose is going to include all of I1, and then every element in I2 that's not in I1 with probability 50%. So as an example, maybe we have I1 and I2. They were both in the original maximal independent set I1. And maybe I3 is connected to I1 in h of delta 1, but it's not connected in h of delta 2. So because of this, we can make H3 part of delta 2. And with 50% probability, we will include H3 as part of S. And the reason why this is nice is because with 50% probability, the size of Nj is actually equal to 1, whereas otherwise the size of Nj will be 0, which is not good, but 50% of the time will be in good shape. Unfortunately, this doesn't quite work. And the reason for this is because if we recall what we want, it turns out that we have an issue when this I2 backslash I1 has a point I2, which is exactly at J. And what actually happens is if we include this point, both the left-hand side and the right-hand side are equal to 0. So as an example here, we could have I1 and we could have I2 exactly at J. And if we include I2, it's not too hard to show that the left-hand side and the right-hand side exactly equals 0. So because of this, we actually run into this like 0 over 0 issues. So even if rho could be, rho could be 1 in this case, or even 0 in this case, but that's actually no good for us. So the method that we have for fixing is as follows, which is we show that in the worst case possibilities of the previous attempt, there actually must be some type facility I3, which is not in I2, but is somewhat close to this small point I2, which is extremely close to J. So specifically, we have, we might be able to have this point I3, which is reasonably close to I2, but not super close. And what the algorithm is going to do is it's just going to replace I2 with I3 with some probability. So now let's just describe how the general algorithm works, which is basically overall, we will create, instead of a maximal independent set S, we will do some sort of very complicated stitching of the independent sets and sometimes allow points to have a single neighbor in this independent set. So what I mean is if we go back, we have these points I2 and I3, which would have neighbors in this conflict graph. And we're not going to include both of them, but we'll include one of the points maybe. So some of these points will actually only be in S probabilistically. For instance, we'll choose either I2 or I3. And even we may just choose neither of them as another option. And we're going to anti-correlate certain groups of very close points so that we don't run into an issue of many close points being there, because that doesn't help the left-hand side, but it's really going to hurt the right-hand side of our desired inequality. So the final set S that we call is a nested quasi-independent set. That's the sort of end result that we create. And the main bulk of our LMP analysis is basically to create a very careful framework based on what the set of points that have distance squared at most alpha j look like. And we heavily exploit the Euclidean structure and look at the sort of possible distances between points based on the Euclidean structure. So to conclude, we are able to obtain state-of-the-art algorithms for k-means and k-median in Euclidean space. Our algorithm is based on the LMP framework of previous works, but we are able to obtain a better LMP approximation. We also are able to show how we can extract the k-mean solution with not too much cost blow-up. In this presentation, I just focus on the better LMP approximation. But feel free to take a look at my paper to see how we are able to get a better k-mean solution from this LMP also. So the main techniques that we're able to use are a new variant of an independent set, as well as a better exploitation of the Euclidean metric. And finally, I would like to mention one interesting future direction, which is perhaps one can obtain a stronger exploitation, one can obtain stronger approximation algorithms based on a better exploitation of the Euclidean metric, for instance, for the facility location problem. And the reason why this is interesting is because the Euclidean facility location and the metric facility location actually currently have the best the same best approximation algorithms. So it wouldn't be surprising if one could obtain better approximation algorithms for Euclidean facility location. So that concludes my talk, and thank you so much for watching.